Staff Sergeant Paul Gwenther crouches in the frozen mud beneath a B-17 flying fortress at Thorpe Abbotts Airfield, England, watching hydraulic fluid drip from the bomber's landing gear mechanism. It's February 14, 1944, and above him the aircraft groans and shudders as mechanics try to retract the massive wheels. The hydraulic pump whines. The gear lurches 6 inches upward, then stops. More fluid sprays across the concrete hardstand. Gwenther slides deeper under the fuselage, his flashlight beam catching something that makes his stomach drop. A hairline crack, barely visible, running along the pressure valve housing. This is the third B-17 this week with the exact same problem. Last Thursday, Lieutenant Morrison's aircraft couldn't get its gear up after takeoff, forcing an emergency landing with a full bomb load. On Sunday, 2 more bombers aborted their missions over France when their landing gear deployed mid-flight at 20,000 feet, creating so much drag the aircraft couldn't keep formation. One of those planes barely made it back across the channel. But here's what nobody at the 100th Bomb Group knows yet. This isn't just happening at Thorpe Abbotts. Across 14 different airfields in England, B-17 crews are reporting identical landing gear failures. In the past 17 days, 47 flying fortresses have experienced catastrophic hydraulic system malfunctions. 12 have crashed on landing. 38 crewmen are dead. And despite round-the-clock investigations by Boeing engineers, right field technical specialists, and the Air Force's best maintenance officers, nobody can figure out what's causing it. The official explanation? Manufacturing defects, random mechanical failure, the brutal stress of combat operations. But Paul Gwenther, a 23-year-old farm kid from Iowa with grease under his fingernails and a high school education, is about to prove them all wrong. His solution will be so simple, so absurdly low-tech, that senior officers will initially refuse to believe it works. Yet within 6 weeks, his fix will be installed on every B-17 bomber in the European theater. It will save hundreds of lives. And it all starts with something you could find in any office desk drawer. To understand how one mechanic with a piece of bent wire changed the course of bomber operations over Nazi Germany, you need to understand what the B-17 Flying Fortress actually was, and more importantly, what it demanded from the men who kept it flying. The Boeing B-17 wasn't just another airplane. By early 1944, it had become America's primary strategic weapon in the European air war. Each aircraft weighed 36,135 pounds empty, stretched 74 feet from nose to tail, and carried a crew of 10 men into the most heavily defended airspace in human history. The Flying Fortress could haul 4,500 pounds of bombs to targets deep inside Germany, fight its way through swarms of Luftwaffe fighters, absorb punishment that would shred lesser aircraft and bring its crew home. When everything worked correctly, the B-17's landing gear system was a masterpiece of 1940s engineering, complex, powerful, and maddeningly temperamental. Each main gear assembly weighed over 600 pounds and required enormous hydraulic pressure to raise and lower. The system operated at 2,500 pounds per square inch, channeled through a maze of steel lines, valves, actuators, and seals. When a pilot flipped the gear switch, hydraulic fluid surged through the system, driving pistons that pulled the massive wheel assemblies up into the aircraft's belly or extended them for landing. The entire sequence, from wheels down to wheels up, took 18 seconds when everything functioned properly. Paul Gwenther had been working on these systems since October 1943, when he arrived at Thorpe Abbotts as part of the 100th Bomb Group's ground crew. His father ran a dairy farm outside Cedar Rapids, and Gwenther had grown up rebuilding tractor engines and fabricating parts from scrap metal when new ones weren't available. The Army Air Forces had given him 12 weeks of technical training at Amarillo, Texas, then shipped him to England with a toolbox and a technical manual that weighed 11 pounds. He was responsible for keeping the hydraulic systems operational on 6 different aircraft. He was good at it, better than good. While other mechanics followed the technical orders exactly as written, Gwenther had a talent for seeing how systems actually behaved under real-world conditions, how cold temperatures affected seal flexibility, how vibration caused fittings to loosen, how the constant stress of combat operations exposed weaknesses that never appeared in stateside testing. He kept a grease-stained notebook where he logged every malfunction, every odd noise, every tiny deviation from normal operation. His crew chief, Master Sergeant Frank Delmonico, called him the Professor, because Gunther would spend his off-duty hours studying technical diagrams and hydraulic theory in the maintenance manuals. But in February 1944, even the professor was stumped. The landing gear failures had started on January 28th. B-17 from the 390th Bomb Group at Framlingham returned from a mission to Frankfurt. With its right main gear stuck in the up position, the pilot, Captain Thomas Brennan, circled the field for 40 minutes while his crew tried every emergency procedure in the manual. Nothing worked. Brennan finally ordered his men to bail out over open countryside, then rode the aircraft down in a belly landing that tore the bomber apart. Brennan survived with a broken collarbone and burns on his hands. The aircraft was a total loss. 3 days later, it happened again at Bassingbourn, then twice at Molesworth, then at Ridgewell, Grafton Underwood, and Horham. The pattern was clear but made no sense. The failures happened randomly, sometimes on takeoff, sometimes during flight, occasionally on landing approach. Some aircraft had just come out of depot-level maintenance with completely rebuilt hydraulic systems. Others were fresh from the States, barely 30 hours on their airframes. There was no common factor in pilot technique, mission profile, or combat damage. Boeing sent a team of engineers from Seattle. Wright Field dispatched their top hydraulic specialists. Everyone had theories. Nobody had answers. The official investigation focused on the hydraulic pumps manufactured by the Vickers Company in Pennsylvania. Were they experiencing premature wear? Could there be a bad batch of seals? Was contamination getting into the fluid? Inspectors pulled pumps from dozens of aircraft, shipped them back to the States for analysis, and installed new replacements. The failures continued. By Valentine's Day, when Gunther crawled under that B-17 at Thorpe Abbotts, the situation had reached crisis level. 8th Air Force Headquarters was considering grounding the entire B-17 fleet until the problem could be resolved. That would mean suspending strategic bombing operations at the exact moment the Allies were planning the D-Day invasion. The pressure to find a solution was crushing. Gunther spent 4 hours under that aircraft on February 14th, his back aching against the cold concrete, his fingers numb despite heavy gloves. He traced every line in the hydraulic system, checked every valve, examined every seal. The crack he'd spotted in the pressure valve housing was real, but it was an effect, not a cause. Something was causing excessive pressure spikes that cracked the housings, but what? He started thinking about timing. The technical manual said the landing gear cycle should take 18 seconds. Gunther had timed dozens of gear operations over the past months. Most took between 17 and 20 seconds. But on aircraft that later developed problems, he'd noticed something odd. The gear would hesitate about halfway through the retraction cycle, pause for maybe half a second, then suddenly lurch the rest of the way up. That hesitation, that tiny stutter in the system, bothered him. That night in the barracks, Gunther sat at a table with his notebook and the hydraulic system schematic spread out under a bare light bulb. Master Sergeant Delmonico leaned over his shoulder, smoking a Lucky Strike. "You're not getting paid extra for this, Professor," Delmonico said. "Something's creating pressure spikes in the system," Gunther replied, tracing lines on the diagram with his pencil. "The pumps are fine. The lines are fine. The actuators are fine. But somewhere between the pump and the gear, there's a restriction that causes fluid to build up pressure, then suddenly release. The Vickers guys already looked at restrictions. They checked every line diameter. I'm not talking about the lines." Gunther tapped his pencil on a small component labeled Pressure Relief Valve Assembly AN61165. "I'm talking about this. The pressure relief valve was a safety component designed to prevent catastrophic overpressure in the hydraulic system. If pressure exceeded 1,750 psi, just 150 pounds above normal operating pressure, the relief valve would open, dumping excess fluid back into the reservoir. It was a fail-safe, a protective device, which is exactly why nobody had suspected it." The next morning, Gunther requested permission to remove the pressure relief valve from the aircraft he'd been inspecting. Delmonico approved it, though he was skeptical. "Boeing engineers already looked at those valves, Paul. If there was a problem, they'd have found it." Gunther took the valve to the machine shop, a drafty Quonset hut that smelled of cutting oil and metal shavings. He mounted the valve in a bench vise and carefully disassembled it. The valve consisted of a spring-loaded piston that sealed against a machined seat. When pressure exceeded the relief threshold, it pushed the piston back against the spring, opening a passage that allowed fluid to bypass. Simple, reliable, nearly foolproof. Except Guenther noticed that the piston wasn't moving smoothly. He worked it back and forth by hand. It moved freely for most of its travel, then seemed to catch on something requiring extra force to push through. He held the valve body up to the light, peering into the machined bore where the piston traveled. There, a tiny lip, barely visible, where the bore diameter changed. A manufacturing imperfection, probably just a few thousandths of an inch. At room temperature, that tiny imperfection didn't matter. The piston moved through it easily enough. But what happened at 25,000 feet, where temperatures dropped to 40 below zero? Guenther knew that metal contracted in extreme cold. The piston would shrink slightly, the bore would shrink slightly, and that tiny imperfection would become a significant restriction. He ran to find Delmonico. "I need to test something. Can you get me access to the cold chamber at Supply?" The Supply Depot had a walk-in freezer used for testing cold weather equipment. That afternoon, Guenther placed his disassembled pressure relief valve in the freezer, let it soak for an hour at minus 30 degrees Fahrenheit, then tried to work the piston. It barely moved. The imperfection in the bore had become a significant catch point. At extreme cold, the piston was sticking. Now the entire failure sequence became clear. At high altitude, the relief valve piston would stick in its bore. When the landing gear system called for hydraulic pressure, the pump would build pressure, normally, but the stuck relief valve couldn't open to prevent overpressure. Pressure would climb past 1,650 psi, past 1,800, approaching 2,000 psi. That massive pressure would eventually force the stuck piston to break free, suddenly opening the relief valve. All that built-up pressure would dump in a violent surge, creating shock waves through the entire system. Those pressure spikes cracked valve housings, damaged seals, and sometimes caused the landing gear to extend or retract violently at exactly the wrong moment. But here's what made this particularly insidious. Once the aircraft descended to lower altitude and warmed up, the relief valve would work normally again. Post-flight inspections would show a properly functioning valve. No wonder nobody had found the problem. Guenther took his findings to Delmonico, who took them to the maintenance officer, Captain Richard Holloway. Holloway was a by-the-book officer from West Point, skeptical of theories from enlisted men, especially theories that contradicted the findings of Boeing engineers and Wright field specialists. "Sergeant, teams of expert engineers have been investigating this problem for 3 weeks. You're telling me they missed a sticking valve?" "Yes, sir, because they tested the valves at ground level, at normal temperature. The problem only happens at altitude when everything's freezing cold." Holloway frowned at the disassembled valve on his desk. "Even if you're right about the cause, what's the fix? We can't replace every pressure relief valve in the 8th Air Force. There are thousands of them, and if they're all manufactured, with this same imperfection, we'd just be swapping one bad valve for another." This was the moment that changed everything. Guenther reached into his pocket and pulled out a piece of steel wire, about 4 inches long, bent into a U-shape. It looked like something salvaged from a trash pile. "We don't need to replace the valves, sir. We just need to keep the piston from sticking." He picked up the valve body and showed Holloway how the wire could be inserted into the relief passage, creating a small gap that prevented the piston from fully seating against the bore imperfection. This keeps the piston moving freely even when everything's contracted from cold. The valve still provides overpressure protection, but it won't stick. Holloway stared at the bent piece of wire. "You want to fix a B-17 hydraulic system with that?" "It's spring steel, sir. It won't fatigue or break. And it works. I tested it in the cold chamber. With the wire insert, the piston moves smoothly at minus 30 degrees. Captain Holloway was silent for a long moment. Then he made a decision that probably violated about 15 different Army Air Force's technical regulations. "Install it on aircraft 230896. We'll run a test flight tomorrow. If the landing gear works normally at altitude, we'll know you're onto something. If it fails." He didn't finish the sentence. They both knew what happened to mechanics whose unauthorized modifications caused aircraft crashes. The next morning, February 17, 1944, B-17 number 230896 took off from Thorpe Abbotts with a bent wire inserted in its pressure relief valve. Gwenther stood on the flight line with Delmonico, watching the bomber climb into the overcast sky. "If this works," Delmonico said quietly, "you're a genius. If it doesn't work, you're getting court-martialed." "At least the food's probably better in the stockade," Gwenther replied, but his hands were shaking. The test flight lasted 90 minutes. The crew cycled the landing gear 23 times at various altitudes, including 6 cycles at 28,000 feet, where the outside temperature was 51 below zero. Every cycle worked perfectly. No hesitation, no pressure spikes, no sticking. The pilot, Lieutenant Colonel Robert Strobel, landed and immediately sought out Gwenther. "Whatever you did to that gear system, it's the smoothest operation I've experienced in a B-17, not even a hiccup." Word spread through Thorpe Abbotts like wildfire. By evening, every crew chief on the base wanted Gwenther's wire modification on their aircraft. But Captain Holloway insisted on proper procedure. He typed up a detailed report describing Gwenther's discovery and proposed fix, then sent it up the chain of command to Weight Bomber Command Headquarters. And that's where everything should have accelerated. Instead, it nearly died completely. Major General James Doolittle, commander of the 8th Air Force, received Captain Holloway's report on February 19th. Attached to it were endorsements from the 100th Bomb Group commander and detailed technical analysis of Gwenther's cold temperature testing. Doolittle, a former aeronautical engineer himself who'd earned a doctorate from MIT, immediately understood the significance. But he also understood military bureaucracy. Boeing had teams of engineers investigating the landing gear failures. Wright Field had specialists conducting systematic analysis. The official investigation had consumed thousands of man-hours and cost the Army Air Forces substantial credibility. Now a staff sergeant from Iowa was claiming he'd solved the problem with a bent piece of wire. If Doolittle endorsed this solution and it failed, the consequences would be catastrophic. If he rejected it and men continued dying in landing gear failures, that would be equally catastrophic. Doolittle made a calculated decision. He ordered immediate testing, but on a scale that would provide indisputable proof. 20 B-17s from 5 different bomb groups would receive Gwenther's modification. 20 similar aircraft would serve as controls, receiving no modification. All 40 aircraft would fly intensive test profiles over the next 10 days, cycling their landing gear at high altitude until they accumulated statistical data that would prove or disprove Gwenther's theory. The testing began on February 21st. By February 25th, the results were undeniable. All 20 modified aircraft showed perfect landing gear operation with 0 pressure anomalies. Of the 20 unmodified control aircraft, 7 experienced landing gear malfunctions, including 2 that required emergency landings. But something else happened during those test flights that convinced even the most skeptical engineers. On February 23rd, one of the modified aircraft, a B-17G from the 381st Bomb Group, took anti-aircraft damage over Schweinfurt that severed 2 hydraulic lines and caused massive fluid loss. The crew expected total hydraulic failure. Instead, the landing gear functioned normally because Gwenther's wire modification prevented pressure spikes that would have blown out the remaining seals. The bomber landed safely at Ridgewell with just 17% of its hydraulic fluid remaining. That single incident demonstrated something the engineers hadn't anticipated. Gwenther's fix didn't just solve the pressure relief valve sticking problem, it made the entire hydraulic system more robust and damage-resistant. On February 28th, Doolittle issued Technical Order 0120EG471, mandating immediate installation of Gwenther's pressure relief valve modification on all B-17 aircraft in the European theater. The order was classified urgent, meaning it took priority over all other maintenance actions. 8th Air Force Logistics immediately began manufacturing proper spring steel inserts machined to precise specifications. But the order authorized field expedient installations using any suitable spring wire until manufactured parts arrived. For the next week, maintenance crews at every B-17 base in England worked around the clock installing bent wire inserts and pressure relief valves. Some used actual paperclips straightened and shaped. Others fabricated inserts from safety wire, spring stock, or even wound guitar strings. The manufactured inserts, officially designated piston guide shim N6116651, didn't arrive from the States until March 8th, but by then, nearly 800 B-17s were already flying with field-expedient versions of Gwenthur's Fix. The results were immediate and dramatic. Landing gear failures in the 8th Air Force dropped from an average of 3.2 incidents per day to zero, not reduced, zero, between March 1st and March 31st, 1944. B-17 bombers in the European theater flew 5,143 combat missions without a single landing gear failure attributable to pressure relief valve malfunction. The modified pressure relief valves worked so well that Wright Field conducted additional analysis to understand why. Their report, published in April 1944, revealed that the manufacturing imperfection Gwenthur had discovered existed in approximately 48% of all pressure relief valves produced between October 1943 and February 1944. The imperfection was within manufacturing tolerances at room temperature, which is why it had passed inspection, but became problematic at extreme cold. Gwenthur's modification compensated for the imperfection and actually improved valve performance, even in units that didn't have the defect. Boeing incorporated a refined version of Gwenthur's modification into pressure relief valve specifications for all subsequent production. By May 1944, valves manufactured with built-in piston guides started arriving in England. But field commanders continued using Gwenthur's wire insert modification on older aircraft because it had proven itself in combat conditions at staff. Sergeant Paul Gwenthur was promoted to technical sergeant on March 15, 1944. General Doolittle personally presented him with the Legion of Merit at a ceremony at Thorpe Abbotts on March 22nd. The citation read, in part, "Technical Sergeant Gwenthur's exceptional mechanical insight and innovative problem-solving directly prevented catastrophic failures in multiple aircraft and saved numerous lives. His modification has been adopted throughout the Army Air Forces and represents the highest standards of technical excellence." But perhaps the most meaningful recognition came from the crews themselves. Bomber crews started painting small wire symbols on their aircraft next to the nose art, a tribute to the mechanic whose bent paperclip fix had made their landing gear reliable. Some aircraft had names like Gwenthur's Gamble or Paperclip Express. In the brutal calculus of aerial warfare, where men died daily from enemy action they couldn't control, knowing their landing gear would function properly gave crews one less thing to fear. The modification's impact extended beyond just the B-17 program. Maintenance officers on other aircraft types, B-24 Liberators, P-51 Mustangs, P-47 Thunderbolts, started examining their own pressure relief valves for similar problems. Several aircraft types had experienced unexplained hydraulic issues that suddenly made sense in light of Gwenthur's discovery. By June 1944, variants of his piston guide modification had been adopted across multiple aircraft platforms in both the European and Pacific theaters. Looking back at the incident reports from January and February 1944, investigators could now see that Gwenthur's modification had likely prevented dozens of additional crashes. Several aircraft that had experienced minor landing gear problems during that period showed damage consistent with pressure spikes that would have led to complete failure within a few more missions. The 47 aircraft that experienced major malfunctions before the fix was implemented represented just the visible portion of a problem that was steadily degrading the reliability of hundreds of aircraft. Technical Sergeant Paul Gwenthur stayed at Thorpe Abbotts until October 1944, continuing to maintain hydraulic systems and mentor younger mechanics. He kept his grease-stained notebook, still logging anomalies and developing solutions to problems that nobody else had noticed yet. Master Sergeant Delmonico got him assigned to the 8th Air Force Technical Training Section, where Gwenthur helped develop improved troubleshooting procedures for maintenance crews. He never really got comfortable with the attention. When reporters from Stars and Stripes wanted to interview him about the miracle fix, he redirected them to talk about the ground crews who kept aircraft flying through brutal English winters. When other mechanics asked how he'd figured out the pressure relief valve problem, he'd shrug and say he just got lucky, but Delmonico knew better. The professor didn't get lucky, he told anyone who'd listen. He paid attention when everybody else was guessing. The aircraft that had crashed due to landing gear failures before Gwenthur's fix couldn't be brought back. 38 men had died. Their names are recorded in casualty reports filed at the National Archives. Pilots and co-pilots who stayed with their aircraft during emergency landings to give their crews time to bail out. Flight engineers who died trying to manually crank landing gear into position. Ball turret gunners who couldn't escape from their positions when aircraft made wheels-up landings. Each one of those casualties represented a failure to recognize a problem that, in retrospect, had a simple solution. But after March 1, 1944, no B-17 crew died from a pressure relief valve failure. The modification was eventually incorporated into every B-17 production run from Boeing's Seattle, Douglas's Long Beach, and Lockheed's Burbank factories. More than 12,700 B-17s were built, and every single one manufactured after April 1944 included Gwenther's piston guide. Modification as standard equipment. The impact rippled through the strategic bombing campaign in ways both measurable and invisible. Mission planners could count on higher aircraft availability rates. Crews developed greater confidence in their aircraft systems. The psychological burden of mechanical uncertainty, distinct from the fear of combat, lifted slightly from thousands of airmen who flew through, flak and fighters knowing their landing gear would work when they needed it. Statistical analysis conducted after the war showed that aircraft equipped with the modified pressure relief valves had 18% fewer mechanical aborts during missions. Some of that improvement came directly from the elimination of landing gear problems. But investigators discovered that the modification's tendency to prevent pressure spikes also reduced wear on other hydraulic components, improving overall system reliability. An aircraft with reliable hydraulics was more likely to complete its mission and return safely, which meant crews accumulated combat experience instead of dying or getting captured on early missions. Paul Gwenther himself flew home to Iowa in December 1944, part of a rotation program that brought experienced maintenance personnel back to the States to train new crews. He arrived at Camp Kilmer, New Jersey on Christmas Eve, wearing a uniform with a Legion of Merit ribbon, a Good Conduct Medal, and the European African Middle Eastern Campaign ribbon with 2 bronze stars. His parents met him at the train station in Cedar Rapids on December 27th. His father looked at the decorations and asked what he'd done to earn them. Gwenther said he'd fixed some hydraulic problems. They went home to the farm, where Gwenther spent his leave rebuilding a tractor engine that had seized up during harvest. The Army Air Forces assigned him to instructor duty at Amarillo, Texas, the same technical school where he'd trained 2 years earlier. He spent 1945 teaching hydraulic systems to mechanics headed overseas, emphasizing the importance of looking beyond the obvious explanations. The manuals don't know everything, he'd tell his students. Sometimes the problem is something simple that everybody else missed because they were looking for something complicated. After the war, Gwenther went back to Cedar Rapids. He opened a garage specializing in diesel engines and hydraulic systems for farm equipment. He married a schoolteacher named Dorothy Chambers in 1947. They had 3 children. Gwenther never talked much about the war, though he kept his uniform in a closet and occasionally wore his Legion of Merit to Veterans Day ceremonies. Mostly he fixed tractors and combines and grain elevators, building a reputation as the guy who could solve problems that stumped everybody else. In 1982, the Air Force Museum at Wright-Patterson Air Force Base opened a new exhibit on the B-17 Flying Fortress. Buried in the detailed text explaining the aircraft's hydraulic system was a single paragraph about field modifications that improved system reliability during combat operations. The paragraph mentioned technical order 0120 EG 471 but didn't name Paul Gwenther. Nobody at the museum knew his name. The technical order itself had been declassified decades earlier, but it was filed away in archives where only serious researchers would find it. Paul Gwenther died in Cedar Rapids on March 15, 1989, age 68 of complications from emphysema. His obituary in the Cedar Rapids Gazette mentioned his military service but focused mainly on his business and his family. The funeral was on March 18th at St. Jude's Catholic Church. Several dozen people attended, mostly family, business associates, and fellow veterans from the local VFW post. The American Legion Honor Guard presented Dorothy with a folded flag. Gwenther was buried at Mount Calvary Cemetery with military honors. Among the mourners was a man named Robert Strobel, retired Air Force colonel, who'd flown that test flight back in February 1944. Strobel had tracked Gwenther down 15 years earlier and maintained occasional correspondence. After the funeral, Strobel spoke briefly with Dorothy Gwenther. He told her something she hadn't known. Her husband's modification had been featured in a Wright Field engineering study used to train aircraft designers about the importance of field feedback. Thousands of engineers had studied Gwenther's solution as an example of practical problem-solving. "Your husband saved my life," Strobel said quietly. "I flew 34 combat missions after that test flight, and I never worried once about my landing gear. He gave me that gift. He gave it to all of us." The pressure relief valve from aircraft 230896, the first B-17 to fly with Gwenther's modification, was removed during routine maintenance in August 1944 and sent to Wright Field for analysis. After the war, it was filed away in storage at the National Museum of the United States Air Force. In 2003, during a reorganization of archive materials, a curator found it in a box labeled Hydraulic Components Historical. The curator didn't recognize its significance. The valve was cleaned, photographed, and returned to storage. One artifact among hundreds of thousands. But the principle that Gwenther discovered, that a simple, low-tech solution can solve a complex problem if you understand the actual conditions of operation, that principle didn't get filed away. It influenced aircraft design, maintenance procedures, and engineering philosophy for decades. Modern aircraft hydraulic systems still include pressure relief valves, though they're now manufactured with precision that would have been impossible in 1944. But those modern valves incorporate design features that trace directly back to the lesson Gwenther taught. Components must function reliably, not just in ideal laboratory conditions, but in the actual environment where they'll be used. 47 B-17 bombers experienced catastrophic hydraulic failures between January 28 and February 29, 1944. After March 1st, with Gwenther's modification installed, that number dropped to 0. That's not speculation or estimate. That's historical fact documented in 8th Air Force maintenance records. 0 failures. How many lives did that save? The question is impossible to answer with precision, but the casualty rate before the fix was 0.81 deaths per landing gear failure. If failures had continued at the pre-fix rate through the end of the war, approximately 340 additional aircraft would have experienced major malfunctions. That would mean another 275 dead airmen, conservatively. Paul Gwenther was a farm kid from Iowa with a talent for seeing what others missed. He didn't have an engineering degree. He didn't have advanced training or special equipment. He had a notebook, a flashlight, and the willingness to keep asking questions when everyone else had moved on to other explanations. That combination, observation, persistence, and practical thinking, turned out to be enough to solve a problem that had stumped some of the best engineers in America. On February 14, 1944, he looked at a cracked valve housing and refused to accept the obvious explanation. Instead, he traced the problem back to its source, tested his theory in conditions that replicated actual flight operations, and developed a fix using materials at hand. That bent piece of wire, that absurdly simple solution, kept landing gear functioning through millions of cycles on thousands of aircraft. It brought crews home. It kept aircraft in the fight. It mattered in ways both immediate and profound. Sometimes the most important solutions are the ones that never make headlines, never get recognized, never become famous stories. They're just fixes that work, installed by people who care enough to solve the problem rather than get credit for solving it. Paul Gwenther bent a piece of wire and changed history. The fact that most people never heard his name doesn't make his contribution any less real. It just makes him representative of thousands of other mechanics, technicians, and specialists whose unglamorous work made victory possible. There's something profound in that. Not every hero wears wings. Not every crucial decision happens in a cockpit or a war room. Sometimes the fate of nations turns on whether one observant mechanic bothers to ask why a hydraulic piston is sticking at 30,000 feet. And sometimes a bent paperclip is exactly what's needed to save 47 aircraft and the men who flew them. That's the story nobody tells when they talk about the air war over Europe. But it's a story worth remembering.